but I think it's time we need to step back and see what EOF could be in the future and what real power unlocks are happening. Now, I named this layer 1, layer 2, and beyond, because a lot of these features we're going to see is going to get some differentiation in a compatible way amongst layer 2s and other chains and other uses, such as off-chain use. But I'm going to focus mostly about what I term as, so I'm an independent contributor. There was a joke in there that I completely forgot about. And that's kind of a lame title. I mean, who do I work for? I work for a company called Numiside LLC, which is a single-person company, so I can be a freelancer and get tax and get health insurance in the U.S. And I can have any title I want. I mean, why can't I just be a senior consulting principal staff engineer? Sounds great. Better than that, I could be the director of execution, verification, and assessment. But I'm just going to stick with independent contributor. So when I think about the future of EOF, I like to think about what's in front of us, what's on the horizon, and what's going to be over the horizon. And you can think of that as what will happen on mainnet, what may happen on mainnet, and what might happen on mainnet, because it's kind of way out there. I'm going to talk about a few things that definitely are going to happen, not in the first EOF fork, maybe in the first EOF fork, but on forks afterwards. And then some things we'll probably see on layer 2 first, and then some things that are going to be experimented with, and if they're really useful, we'll see them come into EOF, into the mainnet. So first, let's talk about what will happen and what's in front of us. And these are focused on things really to make precompiled contracts a lot better and a lot easier, so we don't need to do those anymore. So precompiles can just run the EVM, and you get all the performance that you need. So what's wrong with precompiles? Well, they're bad for client code bases, they're bad for security, and they're bad for project management. They're just really difficult to execute and deliver in a uniform way. It's much better to let people write the code that they want in the EVM and execute it the way they want. The first piece is EVM Max. There was a talk earlier today that went really into depth what EVM Max is about. But what you can think about it is it's math that lets you do stuff on cryptographic elliptic curves a lot easier, a lot faster, and a lot more efficient. And it also lets you do things on curves that are bigger than 256 bits, because that's what your typical security is. It's got some new opcodes, it has a separate memory space, and it helps you move stuff in and out of it. And that's just focusing on the modular. But there's another piece of math that we're probably going to need in the future, in the next 4 or 5 years, when quantum algorithms actually start impacting us. And that is single instruction multiple data operations. And this is for things like lattice encryption, which uses kilobytes arrays of numbers that are stretched out and calculated and computed in large fashion in vectors. And it's inefficient to do this individually. So to really support lattice encryption inside the EVM, we're going to need a lot of different instructions that do it on a vector basis. And these aren't going to be really good for AI inference. It uses a lot of the same stuff, but we're not going to do AI on the chain. So there is an EIP out there. Don't pay too much attention to it. I'm certain it's going to change. This is just a mapping of Intel AVX onto what it might look like for the EVM. There's a chance some of this might show up in the EVM Max proposals. But this is something to keep an eye on in the next 4 to 5 years, because we will need to get some sort of support for vector math to do large quantities of math calculation on the chain. And some of the things that we can do in EOF are to say we're going to need kilobytes or megabytes of memory in the headers, and we can propose to say how we're going to solve those. The last thing that's going to come onto the stage that is definitely going to happen for us for the EVM is legacy and EOF parity. Right now there are a few things that you can't do in legacy that you can't do in EOF that you can do in legacy. Some key support for some smart contract wallets, the ability to bring contracts in from your smart contract wallet into an entry point and bring it in. Right now that's fairly difficult for EOF, but there are some solutions that we're going to solve that. And of course there might just be native account abstraction that would be supported in there. But there's also some features like detecting if you have an EOA that are essential for libraries like OpenZeppelin. Another thing on the horizon that we're going to look at, and this slide speaks as though it's a given, but it's not necessarily a given, is sunsetting as much of legacy as we can, perhaps making it impossible to deploy new legacy contracts. Maybe not. This is going to be a process where we need to make sure that the EOF is legacy for the things we want to preserve and we want to keep. That's the first step, is to get the parity, and then we can start looking at all the other contracts that were deployed before and see what sort of features they have and that are dependent. Can these be brought into a validated sense? Can these be brought in and used within the context of what EOF allows? Or are they going to be doing crazy things like like doing jump locations from call destination, and is it essential that we preserve those? And also, are they doing things like polymorphic code addresses? Do we want to support those or break those? So those are some of the things we need to look for. So the main takeaway from this slide is in a couple of years, we either need to have an in-place plan for how we're going to deprecate legacy and not let new legacy code be deployed, or we need to have an answer of, we can't do this because of reasons X, Y, and Z, and that's okay. And by that's okay, meaning we can still snark all of the mainnet contracts. Just for these few cases, it's going to cost them a lot of money, and we're okay with that. So finally, what are some of the things on the horizon? This is where things get a lot more exciting and a lot more leveraging some of the features inside of EOF. And the key thing is we're enabling better execution on mainnet, and we're going to prove some of these features probably on rollup before they hit mainnets. And they're going to be hitting things like account abstractions. We're going to try unbounding the code size. Who wants to write a contract larger than 24K? That's going to be safe now in EOF, and we're going to show you some of the ways that some of the issues that's going to be affected. And another thing to look out for in the future is concurrency, not just parallelism, but concurrency, being able to take these operations, these contracts, and split them up and run them in isolation safely, which is usually a step for parallelism. Concurrency will feed into a lot of the parallel efforts and make it a lot better. So first, let's look into a native account abstraction. There's actually a proposal out there, and I was speaking with some of the devs earlier this week at a conference we had an offsite. EIP 7701 proposes using some features within EOF to make native account abstraction easier. And the key thing is adding into the EOF container the notion of multiple entry points. Typically, when you run an EOF contract, you have to start at entry point 0. But what they're going to do is they propose putting definitions in the header to say, you know what, you could use section 2, section 3, or section 47, but each of these entry points has a specific role. And when you execute that contract, you're trying to execute it with that role, then you would actually use that entry point instead of entry point 0. What's nice about this is if you have a contract that is validating or serving as a paymaster with entry points, you can be certain that the EVM is only calling those entry points if they're coming in with the role. And you can be sure that it's being used properly from within the system and not just called externally by someone hacking the system with some few random Solidity selector addresses. So there's proposed in there right now 5 different roles, 1 for deployment, and 2 for validation and execution of your smart contract wallet, and 2 optional paymaster validations. And the way that would work is when you're doing a validation for your contract, we would call your contract and keep the role, and if it sees the role has sender validation and it has a separate entry point, we would use that to execute it instead. Same with validation, execution, and post-transactions. This allows us to ensure that this code in these sections only gets called when that role is relevant. Next thing we're going to look at coming up on the horizon is unbounding the contract size. Currently the limit is 24 kilobytes. And this is a size that was set basically during the Shanghai attacks. And it equates to 6 megabytes of gas in about 2017. So it was as big as you can make a contract when the contract size was first imposed, but it was put in as a safety measure in case that there was some other exploit in contracts that people didn't know about. Well, there was one, and putting this contract size limitation in place is actually quite handy. There are some really nasty jump dust attacks that you could do with Create that could really consume a lot of time and space in basically all of the clients. We fixed this in Shanghai by charging every byte that we're going to validate for a contract. So this is not a problem anymore, but if between Shanghai and the Shanghai attacks, it's kind of funny we fixed it in Shanghai. If you would have done this jump dust attack, you would have really caused damage to the network. Now, what's interesting, though, is that EOF validation gets rid of jump dust validation. The validation is performed when you put the EOF contract on the chain. Once that validation is done, you never need to do it again. So looking at this, I mean, it's like, well, what's wrong with 24K? Can we just increase it? Why can't we just increase it to another larger value? And this goes along the argument of saying, well, 640K ought to be enough for anybody. Let's just pick a big number, and we're never going to hit that. It's never going to become relevant. That's the sort of comment that's going to come back and bite us. Even though, as you do research on this, you'll find out that Bill Gates never actually said that comment, even though it's often credited to him. So before we completely unbound it, the size limit is going to be increased, probably double it, and maybe double it again. And even when we unbound it, it's still going to be limited by the amount of gas that you have in a blocker for your transaction. So if you're going to deploy gigabyte size contract, I hope you have a system that allows you to use 1 trillion bytes of gas. And in some off-chain systems, that's exactly what you're allowed to do. Peter Selesky from Geth created a little burnt pixel thing where you can use the EVM to create pictures and render them. And it takes billions of gas. It takes a whole lot of gas, more than you could ever execute on chain. So unbound gas seems to be something we need to be able to handle. But more than likely, we're just going to be increasing the size to more reasonable size to get rid of the problems. Now in EOF, however, looking forward to this, a truly unlimited size does present some problems. There are some natures of the way that EOF is written, that you can only have code sections 64 kilobytes in size, that you can only have 1,024 sections, that your jump destinations are limited to plus or minus 32K from your location. In theory, you could deploy a contract up to 128 megabytes if you have maximum code sections and maximum subcontainers. But practically, the maximum contract size right now is 64K. So how would we fix this? Probably in a few years, when we get to the point where this matters, we'll deploy something called variable length quantities into some of the headers, into some of the opcodes, and make that as an option that contract developers can use if they need it. These headers, instead of being a fixed byte length, would use encoding in the bytes to have a variable length, so you can have truly arbitrarily sized contracts. What's interesting about this is if you're using smaller values, the VLQs actually save bytes. And once you're outside of those, it costs a little bit of bytes. But once you get past 64K, it makes impossibly large things possible. So the downside is that the header must be streamed now. You can't check based on the sizes of opcodes. That might change the way that we validate. But something like this is going to be needed to truly unlock the full size of all possible contracts. And we'll get there just as soon as we can increase the contract size, which is not the easiest thing to get done on ACD. And the final thing that's on the horizon is that I'm personally advocating for is we do a little bit more attention of what we can put in the EVM to support concurrency. A lot of concurrency actually happens outside of the EVM, cross-chain communications, sharding, mailboxes, semaphores, and all that. But there are some things that we can put in the EVM that will actually make some of these concurrency things simpler and allow us to use things like the isolation in the ACID protocol to make these transactions more isolatable. So if you have a bank from if you have a large bank account, you can do all sorts of withdrawals from it in sequence and not lock up everyone from using that account until they process all those transactions. There's two main ways we're going to look at supporting concurrency. Atomic operations, and it's been proposed for deferred execution. Whether we ship these or not remains to be seen. I'm an advocate of at least atomic operations, and there's been some pushback on the deferred operations. We'll see what happens there. But I wrote a proposal, EIP 7519, that solves the basic problems that are needed for atomic storage. Is just have an S credit and S debit opcode, where you can take your storage memory and say add 100, subtract 100. Now that seems really simple and seems really boring when you're looking at it at the EVM level, but the implications are actually in the proof level and in the vertical level, because you're no longer saying take a value from 1 to 2, you're saying take the value and just add 1. I don't care what it is. Just add 1, figure out at the end what it's going to be. And from that, we can split things apart. And we also put in things like having the overflow and the underflow detection in there to make sure that if you're withdrawing money from an account, that the transaction is not going to succeed unless there's actually money in there. This is truly like a bank credit and a bank debit. I mean, this is literally the sort of stuff that you grab an undergraduate database book and you look in the concurrency section, and it's like one of the first examples. Use relative and delta values. So we need to put that into the EVM so that can be possible. The next one that's been proposed is queuing stuff to the end of the block. Was the proposal put up by Micah. But basically taking a transaction, have transactions spawn other transactions. There's been some pushback, but it's the sort of thing that we need to look into, and other chains on L2s and L3s and off-chain may use this feature to have transactions spawn other transactions in other ways. It provides interesting opportunities for out-of-sequence transaction processing. Finally, what are some of the things over the horizon? What are some of the things that are not realistically being planned, but what's some of the great potential that we might be able to do in EOF? A lot of this is adventures in metadata. The EOF header has a rich opportunity to put all sorts of random information about things that may or may not be relevant to the execution, and allow you to do all sorts of interesting things with the values. And that is not something we could do before EOF because we didn't have a good place to put this metadata and read it and understand it and make it safe. So one example is we could, so in order to support this, we could even put into the header to say, hey, we're using experimental EIPs. We could put in a list of the EIPs we use, maybe the version, and maybe some parameters like here's the opcodes where they map to. So you can create these experimental contracts, and you can use them in some EVMs. And the EVMs that don't support those experimental features will be able to read it and say, hey, I don't support this S-credit stuff. I don't support this S-credit debit opcode, so I just plain old won't use it. And we can figure out those things out when you're loading the contract in on the create transaction rather than when you build an entire system and you're trying to use the advanced feature and suddenly you realize that push to 0 is not supported on this VM. So putting that sort of information in the header is going to make it really easy to support experimentation and EIPs and in code going forward. Another thing we could do is we could put alternate bytecode formats. It doesn't have to be EVM in EOF. We could put WASM in there. We could put ARM. We could put RISC-V. It could be the primary opcode, or even more exciting, you could put two versions of the opcode. You could put an EVM version in there, or you could put a RISC-V version in there. So when you're running it on one system, you can run the EVM version, and when you're running it in ZK systems, you can run the RISC-V version. Now, it's going to be on the compiler to make sure that those two versions are equivalent and provide the equivalent systems. But it's a great way to pre-compile and pre-optimize operations on different chip instruction architectures. And when it comes to gas golfing, being able to hand tweak the opcodes in each of those systems is key. Another thing to look forward to is something called progressive precompiles. This is a pitch that was raised on Ethereum Magicians, where they have the idea of, well, let's just take, instead of having precompiles, let's just take all our fancy math and get a standard EVM implementation of this. And then let's feed it through the create to create transaction. That gives us an address. And that way we know that that address is going to be where the opcode is. And let's just make our precompiled code there do whatever the precompile is. The upside is, if you don't have that precompile in your system, you can just deploy the EVM code. And if you do have the precompile, well, it's cheaper and faster and more efficient. The problem comes in that how do you codify what the cheaper gas is in the systems for the precompiles when they are actual local precompiles? And how do you deal with systems that want to prove the EVM execution rather than using the precompile logic and make sure they get the right gas costs? Well, in the EVM, we could specify alternate entry points like we did in 7701. Instead of saying that this is for validation, we could say that this is for the gas cost. And based on the input data, here's what the gas is. So we can go from ancient systems of measuring gas to fancy high-tech versions of predicting gas without having to execute the contract. And again, it's on the precompile developer to make sure that those numbers match up properly. And if systems don't want to use this gas, they can just reject that field and use the EVM execution. Another thing we could do is we could take the Solidity dispatch and we could wire this into the header. In the front of almost every single smart contract is a bunch of switch code where they're trying to figure out from the first 4 bytes where to jump to execute your functions coming in. We could put this in the header and we could just have this as a part of the call dispatch and have it go to one of the different entry points based on your selector. We could save a lot of gas and do it really efficiently inside of the EVMs. And finally, another thing we can do, and this is something that I thought of after I wrote my slides, came to the conference and watched a panel about contract verification. We could put the contract verification data in the metadata in the header rather than just having it as random code bytes at the end of the data section. This is an actual live contract. This is the Tron to USDC Uniswap v2 contract. And you can see they put a lot of metadata at the end that doesn't necessarily have to be used at runtime and could be encoded to say, here's your debug symbols, here's the BZZR link to get the source code, and here's the version of Solidity that we use to compile it. And they could put that in the header, and you could read that, and you wouldn't have to have that exposed, and you could put a lot more semantic meaning inside the EOF header. And this would make people who do validation much, much more excited. So what will be, what could be, and what might be the future, there's what could be on mainnet one day. What will be on mainnet has to do with the EIPs that are already proposed. Things to watch for are account abstraction, unbound contract size, and some concurrency initiatives that are starting up. And the things that might come up is just random plays in the metadata. There are some great opportunities in there. So thanks. Nope, that's not me.
That's not me. That's me. Thanks.
Thank you, Danno. Apparently, you're a man of many hats. All right, for our audience, if you've just joined us, feel free to scan the QR code on the screen to ask some questions. But we do have some already on the Meerkat platform, so we'll start with the first one. Will the shift to EOF impact Ethereum's security model?
So security means a lot of things in a lot of different contexts. When you're talking about the security of a compiled bytecode, it's going to have huge impacts because we can verify the stack heights, and you can be secure about your code. But as far as the security of, like, am I authorized to transfer this DeFi contract to the other thing? It's not going to make anything better or worse on the application layer of people using the EVM. So within the EVM, it's going to improve the security standing, and for people using the EVM, it's not going to make things worse, but it's not going to make things better.
All right, and our second question, any chance for a 64-bit EVM?
There is a chance. Because what's interesting right now, to give some context to that question, the EVM, as everyone in the audience is probably aware of, is a 256-bit register VM machine. And that presents some ahead-of-time compilation issues that you got to play games with the types on the stack. If we dropped it down to 64 bits, there's a lot faster and better code that we could put in. That's the sort of thing that you could, over the horizon, encode into the EVM header that says, by the way, my register sizes are 64-bit, and everything in here operates in 64 bits. I mean, that's an excellent investigation that some L2s might want to do.
Yeah, maybe in the near future. All right, and our last question, which of these proposals would involve changing the EOF version number?
That's an excellent question. So when you talk about version numberings, there's like major numbers and minor versions. And that's kind of some of the heartache that came with making EOF, is we had to do a lot of breaking changes from the initial EVM, things that were incompatible and that you couldn't figure out were different. So everything that I propose here is something that I would call minor updates, soft forks. So if you imagine the world of all contracts that are valid in EOF version 1.0, and you add a feature, none of the contracts in that first set are invalidated, but you grow the set of valid things, I would consider that to be a minor upgrade. And everything that I proposed merely grows what is a valid contract because of the validation. So we're not breaking anything that came before, we're increasing and adding new features. So I don't think anything I propose would require changing the major version number of EOF.
All right, I think that's all the questions we have. Thank